Today we see a very important data structure in design analysis of algorithm called binary search trees. The name itself says what it is good for. It's a data structure which facilitates search among a large database. So you already know what is binary search. But for binary search, you have to keep all the elements in an array. If you remember your binary search, you have to keep all elements in an array. But the problem with the data structure is you cannot grow the array once you define it. Suppose the data are inserted or deleted, you cannot modify your data structure because you have to declare your array size at the beginning of your algorithm. So it is not a dynamic data structure. So in one thing you require this array for binary search, and also you want to have the facility of deleting and inserting elements into the data structure. The solution between the two, which merges the efficiency of both of this, is these binary search trees. So these binary search trees allows you to search elements, to store elements in such a way, with the key values, such that you can search an element very efficiently into the data structure. And at the same time you can insert, delete data items into the structure very efficiently. So let us see, I will not go into the details of this binary search tree structures because most of you had some experience with it in your data structure course. So I will just, most of the time I will recall some of the major features of this data structure. So first of all, let me just tell you what specific representation we are going to have for this. So let me draw a binary search trees. So suppose all my key values are integers. The major feature of a binary search tree is this. If you have a value, say here, say 30, each node, since it is a binary tree, has either one or two children, left child and a right child. All the elements in the right child and its subtree, all the key values in the right child and its subtree will be greater than the key value kept in the node. So I can put it here, say probably it was 40. Similarly, all the key values kept in this left child and its subtree below this left child will be less than the key value of 30. So I can put probably 20, say if I recurse on this definition, I can put say 10, say probably this one was 25, this one was say 22, this one was say 27, say this one must be greater than 25 and less than 27, so let me put 26, this is say 28. So this is a binary search tree. Now, the way it has been kept, it facilitates your search a lot. How? So basic idea is, suppose you are searching for elements say 15. So you first check at the root whether 15 is less than 30 or greater than 30. It is less than 30, immediately you know if it is at all present, it should be in the left subtree because you know all the elements on the right subtree are greater than 30. So we can eliminate searching in the right part totally. We can only search in the left part. So you can take this path, then 15 is less than 20, take this path which is 10, 15 is greater than 10 but there is no right child of 10, so that means 15 is not present in this case. In case you are trying to find out say 25, you will just take this path and come to 25 and declare 25 is there. So the way we have kept this binary search tree, the elements that facilitates this search efficiently. Now let me just, this is our notation. For each node we have always two children. Alright. Now one child may be empty. Okay, and we will denote the empty children with say squares like this. So this node probably in the declaration it has 2 pointers, one is left child and right child, these 2 pointers will be null. So this time this one also has 2 empty, this one has 2 empty pointer, this one has 2 empty pointer, this one has 2 empty pointer, and in this case actually there is no node with one child. In that case that will have only one empty pointer. Okay. So this is our convention that every internal node, so every internal node will have exactly 2 pointers, left and right child. And what is the definition of a leaf? A node is a leaf. So a node is a leaf if both pointers, both children are empty. Right? So this, according to this will be a leaf. So probably this is the definition you have seen already. But let us, we will assume this is not our convention. What we will assume that these are the leaves, the empty pointers. Everything else is an internal. That is just our convention. Alright? So don't get confused. In many books or other texts you will find that sometimes people declare those internal nodes with 2 empty pointers are leaves, but we are not assuming that. We are assuming that these empty pointers, they are basically leaves, all the other nodes are internal nodes, just our convention. Okay, so this is we are not going to follow this. Okay, I don't have to define what is descendant. What are ancestors? Basically 25 is a descendant of 20, even 30. 30 is an ancestor of 25. Those who are coming below a node in the subtree, mind that I cannot say that say 27 is a descendant of 40. It's not coming into the subtree of 40. So 25 is a descendant of 30, not for 40. So I don't have to. So these are the very usual terms: descendants, ancestors, height of a tree. Basically, height of a tree is first you take the maximum depth of a leaf in the tree. What is the depth of a leaf? The number of edges you have to traverse to come to that leaf from the root. And maximum depth will be nothing but equal to the height of the tree. Height and depth. Now let us see some common operations we can do on a binary search tree. So one of the very common operation will be traversal of this binary search tree. We want to traverse all the nodes in a very specific order, suppose. So one of these traversal is called the in-order traversal. So I am going to write what it is and then it will be clear what it is exactly doing. So mu, I will denote mu as a pointer to a node. Now this in-order, this routine will be a recursive routine. So we are going to pass a node to it. Initially this will be called with the root node. So what is the in-order traversal? So let me go back here in the previous example. In-order traversal, while traversing a node, you first traverse its left child, then traverse this node, then traverse its right child, and do it recursively. So if we do this one here, 30, I cannot, when I say traverse, basically you cannot print that value. We want to ultimately print the values in the nodes. Don't print that value now because it has a left child which has to be traversed first. Go here, then that also has a left child, so go here, 10. 10 does not have a left child. So now you print 10. So in order traversal it will print 10, then it will go back. It will print 20, its parent. Then according to our rule, it has to print its right child. It has to traverse its right child 25, but before 25 is print, its left child should be print. So come here. So we are traversing this, then we are going back and coming here, 22. Then 22 is traversed, then 25 will be printed, then 27 will be printed. Where is it? Where is, oh, sorry, I forgot. Sorry, I thought that it's ending here. It's not. Okay, yes, you are right. So this will be printing 26. Then 26 will be printed. Then 27 will be printed. Then 28 will be printed. It goes on. It will come like this. Basically, you are just wrapping a thread around the tree. This algorithm, it goes on, okay, I didn't complete. So this is the in-order traversal of this tree. So the pictorial way of looking at it, as if you are wrapping a thread around the tree. And the length of the thread will be twice the number of nodes, almost, roughly equal. So let me write down this procedure in order mu. If mu is not equal to nil, that is a null pointer, then you have to call this in order on what? Mu dot L. That will be our notation. Mu dot L will be the left child of mu, and mu dot R will be the right child of mu. Then you print. So this, when this recursive call has come back, it has finished its printing. See, this will not print probably mu dot L, it will probably go on in a recursive call, like in the picture. And then ultimately it will come back. So in this picture what it means, we gave a call here, it went all the way up to here, it printed, it came, ultimately it printed everything, then it came back here. So that's the point. We will be printing 30. So print here mu dot key, key is the key value, the elements which are kept in the node mu. And then what should we do? Again another in order traversal we have to do on mu dot and end this. So this is the in order traversal of a binary search tree. So if you do an in order traversal of a binary search tree, the values which will be printed, they will be in what? Alphabetical order or? It's in an ascending order. So like here, you will get 10, 20, 22, 25, it will be sorted basically. Once you do an in order traversal of a binary search tree, you will get sorting of all the numbers. Now how much time does this take, this recursive call? We have to call it with the root node. So how much time does this algorithm take in total? Order of? What is n? So how can you argue that it is order of n?
Number of edges.
It's not visiting all the nodes in that way once, because it's coming, when it's coming back, it's again mu dot key, it's printing.
It's almost twice the number of edges.
Yeah, it's because of this logic I told you, as if you can see this entire algorithm as wrapping a thread around the tree, and the length of the thread in terms of the node is not more than probably twice the number of nodes, or maybe thrice, it doesn't matter. But it's constant time. What you should say that every node will be visited constant time. Once or twice, don't commit yourself. You don't know exactly. But constant is a very safe thing to say. You are visiting a node constant time, twice or thrice. So that means this is order of n. Now tell me, I am asking one question. Now with an order n algorithm, we are getting a sorting. How is that possible? We already know sorting cannot be done in less than n log n time. Yes, that's very good. So the point here is you have already created the tree. And this tree, so that automatically tells you that creation of this binary search tree cannot be done less than n log n time. No log n. What log n? N elements you have to spend n log n. There should be no doubt.
If I can do less than n log n, by this algorithm I should be able to sort n numbers in less than n log n, but that is not possible. So it says you have to spend at least n log n time to construct the binary search tree of a set of n numbers. So similar to in-order, there are other way of traversing the binary search tree, which are called pre-order and post-order. So what are the rules here? I will not give you the algorithm, probably you can write it immediately. In pre-order, you first print the key value of the node, then left child, and then right child. So you first print out the value at the node, then you print the value of the left child, then you print the value of the right child. So that is pre-order. Why it is called pre-order? Because before you are visiting left and right child, you are printing its own value. That's why it is pre. So similarly, what should be the post? Just the opposite. So print left, then right, then the node. So basically, this call, the order of this call should be regulated probably. So these three, print, in order, in this case. So in case of pre-order, it should be pre-order mu, all this remain same. Then you have to do print mu dot key, then pre-order mu dot l, pre-order mu dot r. And in case of post-order, just do first post-order mu l, post-order mu r, then print. The order of these three statements just gets commuted to get three different way of traversing this tree. Now, I just state one property which can be verified later. You verify it later. I just state it. Suppose you want to know whether given two nodes, so suppose we have been given two nodes mu and another node say gamma or nu. So mu is an ancestor of nu if and only if this is valid, that pre-order, basically this is the ordering. If you, while traversing the tree, if you order the nodes according to your traversal, that gives a ordering, a number to a node. So I'm referring, when I say pre-order mu, it means that number. If this is less than pre-order nu and post-order nu is greater than post-order, you verify it later. If these two conditions are satisfied, then you know that the mu is an ancestor of nu. And it's an if and only if condition. Alright? So what you can do, you first traverse the tree in a pre-order fashion, traverse the tree with a post-order fashion, and then label the nodes according to your traversal. So when I say pre-order mu, that means is that number when you traverse it. Suppose you start traversing the node with 1. So in this case, so in first case, so our traversal number in this case, this will be traversal number 1. The way you are printing, that will give the label. So in post-order and pre-order also you can get the same sort of labels. So when I say pre-order mu, it means that label. So mu is an ancestor. You can see why it is to be true, because if it is an ancestor, it has to be visited in pre-order fashion first, then mu. And in the case of post-order, it just should be the opposite. So one direction is easy, but why? If this is true, it should be ancestor, then it's a little bit of. Alright? Now, let me just give you the algorithm for searching on a binary system. I'll just give you the C group for searching binary systems. And I already told you how to do it. So function search so I am going to search the value x in the tree. Since this will be again a recursive call, I have to supply a node pointer to a node. So initially this will be initially what? Initially it will be root. Okay. So what is the first you in any recursive call, as we know, first you have to check the boundary condition. If mu is equal to nil or x is equal to mu dot key, basically you have found it. This means you have found it. In both these cases you have to quit this algorithm. In this case that means you have not found it. In this case you have found it. So then return mu. See, this you can handle both cases uniformly. If this algorithm returns a null pointer or nil pointer, and if mu is nil, you are returning nil. That case you can say that if it is a null pointer, it was not present. Otherwise, it will return the pointer which is the node which is containing this value x. Else, if x is less than mu dot t, then we have to give a recursive call. So what do? You give the recursive call search x mu dot left. Else search x mu dot r. And if you can say return. You can say here also return. If you are very careful about your syntax of your program, I am not bothered with the syntax of how you write it. Okay, these are implicit, right? Return. End if. Now here also another end if. So that's it. This is your algorithm for searching an element. Either you go to the left or to the right of the tree. Okay, node. Now can you tell me how much time does this take? Order of? Some people are saying order of n, some people are saying order of log n. But I am not getting the correct answer yet.
Worst case order.
Still I have not got the right answer. You cannot say worst case. You can definitely say order of
In log n.
no. After going through all this, you should not say order of h. Yes. That's the correct answer. You should say order of h, where h is the height of the tree. Why should you commit again? Whether h is n or log n? The better answer will be order of h. When h is the height of the tree, so order of h, where h is the height of the tree. We'll see. See, in the worst case binary search tree, if you are not keeping it balanced, it may not have, h may not be log n. It may be order of n. So one thing you should keep in mind, binary search tree does not guarantee you that it will be automatically the height will be log n. Okay, so that's the common mistake people do. Binary search tree, height is log n. No, it's not. You can have a tree which is very skewed, the entire height is order of n. So you have to keep the height or keep the entire tree balanced, then only you can guarantee that the total height will be order of log n. Okay, but I have not done it in this all this algorithm that balancing. So I can only say its height is complexity is order of 8. Now there are other types of applications or other functions which are generally use this binary search tree. So one is this search. Then we can also use the binary search to find the minimum. This is so first operation was search. Second operation I can use to find minimum. So what do you do for minimum in the binary search tree? So you go to left unless you see the null pointer. And that you know by the property of the binary search tree, the leftmost node will be the least element. I don't have to write that algorithm. So this is, I know, order of h already. Now how much time this one will take then? Minimum? Again order of h. It cannot be more than the height of the tree. Now next function can be successor. What is successor? Suppose you have been given an element. You have been given an element, okay, or integer number which is present in the tree. You need to know what is the next element. If I would have sorted the numbers in an increasing order, what is the next element which will occur in this list after this number? That is called the successor. Successor in the list of increasing number. So you can again use this binary search tree to get this function successor. So let me just tell you, let me take an example. So I'm just going to take an example. So let me put some, say 20, 10, 5, 12, 11, 18, 40, 41, 30, 35, say this one is 25, say something is there, say 8, or I cannot say 28, say 24, say 23. Okay, so suppose the binary search, this is a binary search tree, and we want to find out what is the successor of 18. So I'm not going to write the algorithm pseudocode for you, but I will tell you the algorithm. You should be able to write it. What do you do? First you check whether this has a right child. It does not have a right child. Then you go back. As long as it is taking, while going back, it is not taking any right turn, you just go back. The first time it takes a right turn, that is the node which will be the successor of 18. Because this is the node actually which will be visited in the in-order traversal next after 18. So 20 will be the successor of 18. Or if, say, let's say, what is the successor of, say, 20? Suppose it has a right child. I want to know what is the successor of 20. Then you go to the right child and then go to the leftmost node, 23. Then 23 will be the successor of 20. So these are the two cases. You can handle these two cases again in how much time? Order of h, because you are not traversing more than the height of the tree. Now the fourth function, which we will see, insertion of a node. So I am going to write the function for inserting a node. So what do? For inserting the node, first you find the position of that node. So suppose I want to insert, say, which is not there, say 35, 39. So I go here, it is less than 40, go here, greater than 30, go here, greater than 35, no, it's not there. But I know then 39 has to be the right child of 35. I put it there. So that's the insertion. So I'm going to write it, what I just told you. So procedure insert so this is the root of the node, root of the tree. I need this pointer to be passed. So initially we are calling it with root. Actually this will remain. This time I am not going to write this insert in a recursive fashion. I am going to use the algorithm in a iterative fashion, just for a change. You can write it with a recursive manner also, just for a change. And this is the node which has to be inserted. The pointer has been given. So initially I just use a variable x is equal to nil, mu is equal to set to root, while mu not equal to nil, do x is updated to mu. If new dot key is less than mu dot key, then you should update mu to what? If mu dot key is less than mu dot key is less than mu dot key, then mu should be updated to mu dot L. Else mu is equal to, you go to mu dot R. So that is end if. And you just end while here. So this loop basically will traverse down the tree and it will go up to the leaf or the last node, not a leaf, I should not say according to our convention, it will reach the last node which has both pointers null. Now you just set up properly. New dot p is equal to x. X is the node actually, basically, that's the way we have set up. X is the last node. So we are going to attach new to x. So its parent will be x. Now I have to put x to the right child or left child, that I have to test. If x is equal to nil, so it can happen that the tree itself was null. Then x will be nil. In that case, your root will be set up to this new node. This is the first time you are inserting something into the node. That case is taken care of here. Okay, so this is the boundary condition. Else, if new dot key is less than x dot key, then obviously x dot L is equal to new, else x dot R is equal to new, end if. And that's it. Just end if. Okay. So this is a very simple algorithm again. Insertion. Insertion is basically like a search. Just you have to attach. So how much time does this take? This algorithm, entire algorithm? Again order of h. So now you can see a lot, almost anything you want to do on binary search tree depends on its height. So to achieve something efficient, you have to keep the height of the binary search tree as low as possible. And that is done by the balanced binary search tree, which we will see in the next lecture. But before I go to the next lecture, let me just go over another operation which is not so difficult, but it requires some care. So which is called a deletion. We have just seen how to insert a node. Suppose instead I want to delete a node. I want to delete a node, what to do? So again I take an example and tell you what to do, but I will leave to you how to write a pseudocode. I will not write a pseudocode for you. But I will give with an example, I will tell you the method, all the cases. So I am drawing one, so say this is 20, 10, 40, 30, 41, 35, 25, 28, say this one is 24, say this one is 23, this one has 5, this one has 12, this one something, this one say 15, say let us put 11. Suppose this is the binary system and we want to delete a node. Now there are several cases. Case 1, the node to be deleted has no children. I mean does not have any children. I mean, according to our notation, its children are empty. It has children, but both children are empty. So if that is the case, so let me take something like this, say 23. Both of his child is empty. So what did you do? If I tell you to delete this node, what did you do? How would you delete? Just cut it. Basically you cut it off from the tree. So basically you say the node which is containing 24, its left child to be null. Or you just cut it from the tree. No problem. It's the last node. No children. Okay, so this is the easiest case. Case 2. Node has one child. So let's take 24, this one, the original tree, suppose this one or not. So 24, we are required to delete this 24. What would you do? It has only one child. Right, so what you do, you just take its children, the only children, and set that children's parent pointer to its own parent pointer. So this will be pointing to basically this. So 25 will be linked to, so this will be bypassed, basically bypassed. Case 2 will be that. You can bypass this node. This can be done very easily. Again, it's a matter of setting. If a pointer has been given to this, it's a matter of setting the pointers. Nothing else. It's a constant time affair. If a pointer is supplied to it, but if the pointer is not supplied and the key value has to be searched, then it's again you have to search the key value first, get the pointer, then do this. Now there is one case, that is the when node has both children. Like I can take the root. Like suppose I say that delete this node. It has both children. What would you do now? So what you can do, you first find out its successor. We know how to find out the successor of a node. So in this case, our successor will be 23. Exchange this 23 with 20. So 20 just deletes, and 23 comes here. Say 20, you can bring it here. Just exchange. Okay. Now we are going to delete this one. So this is the case 1 actually now. You are guaranteed if you take a successor of a node, that node must be having no children. Or one child. But you can always go back to case 1 and case 2. Okay? So you can always go back to, you can solve, after you do this, you can go back to case 1 and case 2. It will never happen that successor of one node will have 2 children. It can never happen. You find it out why. That is left to you. No, it does not depend. It will never happen. It will never happen because the way we have defined is either extreme left or it is extreme right or something like that. Find that the node we are going to delete has two children. So its successor will be nothing but go to the right and then take the leftmost, and that cannot have any more children. Okay? Either it does not have any more children or one child. It can have one child. That's fine. Yes, that's what I'm saying. Either it has no child or it has one child. But we can go back to case 1 and case 2 in that case. So that's the way you solve this 2 cases. Actually, instead of taking successor, you can take the predecessor also. The function we define successor, you can easily modify how to write the predecessor of it. That will be a good exercise for you. What should be the rule to find out the predecessor of a number in a binary system? It should be very similar to successor actually. And you could have replaced the predecessor also with this, and then you just delete that. Okay. Why the third case we are doing like this? You remember, you can see by doing this we are not disturbing the binary search structure actually. We are going to delete this, but this node comes here, which is its right position actually in the binary search tree. So this is a valid operation. Now how much time does this take, this entire deletion? Order of. So we have seen in binary search tree all the operations, all the important operations are taking order of H time again. So H is very important. So next we will see in the next lecture how to keep this H low. That is of the order of log n. That will be our desirable complexity. That the height of the tree is kept log n, no matter how we delete or insert some. Basically, while inserting and deleting, you have to keep track that the height is okay. You have to make some bookkeeping or something you have to do. You cannot just naively insert or delete elements. We'll see that one in the next lecture. There are several trees structure or several types of trees which take care of this, but we will study one of them, which is called the pipeline.